Okay, let's finish our CPU. To do it, we need to do only some finishing touches. Maybe I'll move around some blocks here to have them in a little bit more favorable order. So for example, random access memory signals, I will, wait a minute. I will move everything a little bit down. And then these write enable and read enable signals, maybe I want to move to the opposite side where it's data to RAM and value from RAM. To do this, I will change the signal to face west. And move it here. Oh wait, I changed the label location. So east and west. Oops. So this is right, read enable random access memory. And for this, we'll do the same thing. So I'll just move it here, facing west, like this. Okay. Down 1 second. Like this and this, like this. Okay. These signals can be moved back up like this, and let's continue. So from the point of view of our processor, we need to control flash memory with two signals. One of them is data coming from flash, and the other one is address of flash to which we want to access. So program counter is the one that determines this flash address. So I will create a new output, which will be 8 bits. And it's it will be facing east. The input will be on the east side, like this, and its label will be flash address. For example, like this. And its location will be, for example, north. So with program counter, we ask for data from flash, from, for example, address 0. And in this flash data, we receive from flash the instruction. Okay, so next signal is clock. We have clock right here, but for maybe a bit better visualization, we will move clock to the bottom. It will be more beautiful at the end of our CPU setup. So I'll put clock down here. So this is clock, this is inverted clock. The second signal that we need to also add is reset. Reset pin is an external pin to the CPU. When we press it, program counter is reset to 0 and general purpose registers are reset to 0, and also status register is reset to 0. And actually we have reset signal here, so I'll just move it, for example, down here. Like this. And it will be facing west, sorry, north. Okay, so I press reset and general purpose register is reset, program counter is reset, status register is reset, other signals are not touched. There's nothing to reset. Okay. Next thing is, let's see. status register here. Okay. Signals address from RAM, data to RAM, and value from RAM are here, right? Enable RAM is there. So now, basically, our CPU, our microcontroller is almost done. So now we can try to connect this CPU to flash and random access memory. To do this, we will create new sub-circuit project, add circuit, and this circuit name will be MPU. And here's the difference between CPU and MPU. CPU is the core, the processor, and the microcontroller or microprocessing unit is basically CPU plus flash plus random access memory. So inside our MPU, we will insert CPU with just one thing. We need to edit its schematic symbol. And let's do it. And I will just make this element a little bit bigger, that's all. So I'll make it, for example, this big. I'll put these pins here, clock and reset like that. And I'll just put a text with big letters CPU in the middle. So this is our CPU. Maybe move these signals like this. Okay, so this signal is data from flash. This is address to flash. This is clock. This is reset. This is, I guess, read RAM. This is write RAM. This is data in, data out, and address out. Okay, so in our microcontroller, MPU or MCU, call it whatever you want, we insert the CPU, and now we have to connect it to the memory. So under memory, I find, in our case, read-only memory. So flash memory, the program memory is read-only memory, and here it is. And now we will configure them. So our address will be 8 bits because our program counter is 8 bits. So the address will also be 8 bits. And our data content will be 16 bits because each instruction is 16 bits wide. So it's like this. Data is 16. So I connect data out of flash to flash data in, and address I connect to program counter output right here. Okay, so let's test it. I will write some value here. So I'll write, for example, 1, 2, 3, 4. Wait, 1, 2, and 3, 4. So in this case, read-only memory cells are 8 bits. But when I select, for example, cell number 0, actually 2 cells are forwarded. So let's see, edit contents. Like this, and the contents are here, and they will be forwarded to CPU. So initially it didn't show 8 bits, but you have to click project, simulate, reset simulation, and then this flash memory updates to become 16-bit memory. Before it was 8 bits, it's some glitch here. So the data is forwarded to processor. Next, we need to connect random access memory, and there are actually several kinds of random access memory. We will be using the simplest one to connect. So one, we will select this separate load and store ports because it will be just easier to manage it. In reality, most random access memories have just one asynchronous load or store port, but we will not use it this time because it's a little bit more complicated to configure. So let's connect the signals. Address of RAM. We can just connect CPU tells the address. Oh yeah, and we have to configure it. Address bit width will be just 4 bits. We will have just 16-byte random access memory, and the content will be 8 bits, so 8-bit. Next signal from CPU is value from RAM, and this is the data that is going into the random access memory. And the third signal is, sorry, I think it's the other way around. This data is data that's coming out. So this is data from RAM, I think so. Data value loaded from address, and this is value to be stored at address. So data to RAM goes like this. In reality, there would be a 3-state logic, which works both ways, but in our logsim, we will not do it. So, and the next one is read enable RAM, and the second is write enable RAM. So we need to check out the meaning of these random access memory inputs. So one is clear. We will put a small button for easier management of this CPU. So I'll just put a small input facing west to this clear, but in reality, CPU random access memory is never cleared by external force. So when you turn on the CPU, random access memory can have some random values in them if it's not initialized, or it can be just old values from previous runs. So in our logsim, we will just reset it to do it faster, but in reality, random access memory is not guaranteed to be reset. Next signal is load. So this is like a clock output to output data on this data line. So the way we will connect it is the following. If read RAM signal is high, then output data to this data line. So this is our signal, read enable random access memory, and when it's high, we want data to be output to data line. Next input is store, which we will connect to write enable. So only when write enable is high, we store the information from CPU into data. And then we have also select signal and clock signal. So memory value updates and rise from 0 to 1. So we'll connect it to clock, and therefore we need to also put a clock signal here. Clock signal is under, I don't know, input output. Where is it? Clock. Cannot see it. 1 second. Clock, here it is. Okay, so we have a clock signal facing north. It is, of course, it's like, for example, an external oscillator. It's, of course, connected to CPU, but remember, we also have to connect it to clock input of this random access memory. Just one thing you have to remember, writing happens on falling edge of clock. This needs rising edge, so we invert the clock signal like this. So on rising edge of the clock, nothing happens, and on falling edge, if there is the data and if writing is enabled, then on falling edge of main clock, which will be rising edge of this signal, value will be updated in random access memory. And then chip select disables component. So to make sure that some random signals are not traveling around random access memory, we want to disable it as long as both of these lines, write enable and read enable, are low. So only if one of these lines is high, we enable random access memory for access. So we will just add an AND element here. Oh, sorry, not AND, but OR. So I'll put an OR element here facing north, data bits 1, gate size narrow, inputs just 2, like this. So only when read enable or write enable is high, random access memory is enabled. Okay, I'll put it more beautifully here, like this. Okay, so this is our connection CPU to random access memory. And one more thing is the reset button. So this reset button will be separate from random access memory. Reset facing north, label will be reset. Its location will be, for example, east, and it's just connected to CPU reset. So this signal clear, we will not use it. Reset happens with this button. I click reset and CPU is reset. And then when I do the clock, then CPU is working. Okay, let's check out if the CPU is working or not. I don't know. But the way that we can test if it's working or not is by writing some instructions and checking if they are performed correctly. So let's go to our microprocessor unit and write some instructions to test our CPU. So first we want to load two numbers into CPU. We can do it using LDI instructions. And maybe I'll write it in Notepad. Just plain Notepad. So first thing that I want to do is, for example, load value into register. We do it using LDI instruction. Load immediate, for example, into register R0, value 5. Next we want to do is load into register R1, value 6. Then we want to, for example, add R0, R1, which means that R1 value will be added to R0 value. Then we also want to compare register R0 to R1. Then we also want to branch if, for example, 0 flag is set to address 0. For example, if 0 flag is set, jump to the beginning of the code. Otherwise, we want to store value of register R0 to random access memory address 3, and then we want to load into register R2 value that is stored in memory location number 3. So with this test code, we could, for example, test almost all instructions that our CPU can perform. So let's try to translate it to machine code and run it on our CPU. So to do that, we need this table that we built last in the last lab. I guess it was here. Oh no, it's the other one. So instruction set quick reference. LDI instruction is 0010. So I will write it like this 0010. Next is source register R0. And then number 5, 00000101. So this is the machine code of this instruction. Next one is load immediate R16. It will look the same. Register will be 0001 and value will be 6. Like this. Next is add R0 to R1. Add is arithmetic logic unit instruction. So first 4 bits are 0, then is register R0, it's just zeros. Then add is instruction number 0 under arithmetic logic unit, so it's just 4 zeros. And then register R1 is just ones. Compare instruction 0001. Destination register will be, for example, R0, so it's just zeros. Instruction will be subtract, so it's 5. Then register R1. Then it's branch if 0 set. So branch if 0 set will be branch is 0110. Condition is branch if equal, branch if 0 set. So 0 set means that the two numbers are equal, so it's branch if equal, so it's 5. So condition is 0101. About these conditions, we can talk a little bit later or in lectures. Now you just have to believe me that it's 0101 and address will be 0. So if these is if flag 01 is 1, then branch. Next instruction is store. Store is 0100. So it's ST or ST to random access memory and LD or load to random access memory. So store is 0100, then register number 0, and then address to which we want to store 00000011. It's number 3. And load register load from random access memory into register R2 from address number 3. LDR is 0011, register 2 is 0010, and address is 00000011, like this. So this is how we write in assembly language, and this is how we can translate it to machine code. Let's now put these values into our flash memory right here. The only thing is flash memory accepts hexadecimal numbers. So we need to be able to quickly convert these numbers to hexadecimal. But it's not actually that complicated because in a binary world, every 4 bits become 1 hexadecimal symbol. So maybe I'll copy it as text here. It does not accept multi-line text. That's sad, but fine. Okay, here's the label. Oh, this one is also just single line. label text tool, nothing. Oops, nothing happened. Okay, so we cannot really input multi-line text. So I'll just use Alt Tab. So let's translate it to hexadecimal. So 0010 is 2, 000 is just 0, next is 0, and 101 is 5. Next one is, this is 2, this is 1, this is 0, and this is 6. 0, 0, 0, 1, 1, 0, 5, 1. Next one is 6, 5, 0, 0. Next is store. This is 1, 0, 0. It is 4, 0, 0, 3. And this one is 3, 2, 0, 3. Okay, now I'll write these numbers into flash memory. So we can do it by clicking on this and selecting edit content. Then I can have these both windows open side by side. So the first instruction translates to 2005. Next one is 2106. Next one is 0001. Next one is 1051. Then it's 6500. Next is 4003. Next is 3203. Okay, and then I exit this window, and here we can see the contents of the flash memory. And now we have to just check out if our CPU is built correctly, if we're geniuses and we have built an actually functioning CPU. So let's do it one instruction at a time. So when I click, first of all, if I have just input this flash code and reset the CPU, initially, as you can see, nothing's happening. Flash data is already showing the first instruction, which is 2005, because this read-only memory is like a lookup table without clocks, so it's immediately outputting whatever you select with the select signal. So it's already outputting the first instruction, but instruction register only photographs it on rising edge of the clock. So the rest of the signals, I don't know, it's just all zeros. So when I click rising edge of the clock, when I go into CPU, we can see that the instruction register photographed this instruction and is holding it, and it will be holding this instruction here for as long as we have falling edge of the clock and the next rising edge of the clock. Only then this instruction will be updated so that there's no randomness here. And all of these control signals have been forwarded to all blocks of this CPU. And on rising edge, we only photograph instruction and forward it. So if I go into each element, it's still zeros. There is some data coming in. For example, 101, which is 5, is already coming into general purpose register, which is good because we wanted to load 5 into register R0. And if we check out the address select signal, it's 0. So it's ready to write this 5 into general purpose register address number 0, but it will only do it on the falling edge of the clock. So I went to the microcontroller MPU view, clicked on the clock to have it falling edge. And as we can see, in our general purpose register number 0, 5 was stored. Also, what you noticed is this black background jumped to the next instruction, because when we on our program counter, it was displaying address number 0, but it was fed through this adder to point to address number 1, and jumping was disabled. So on falling edge of clock, program counter automatically incremented by 1. So now it's pointing to the next flash address, number 1. The next instruction has already arrived to our processor. And on rising edge of the clock, instruction register will photograph this instruction and be ready to execute it. So on rising edge, all signals arrive to all blocks. So in general purpose register, number 6 arrives and address number 1 is selected, because our instruction was load the number 6 into register R1. So number 6 is here, register R1 is selected. Also inside our CPU, program counter shows 1, but its input is already 2, ready to be updated on the falling edge. So when I do the falling edge of the CPU, all of the signals are applied, written, so register number R1 shows 6, and our program counter has incremented from 1 to 2. Okay, so this is a very smart way to do it. And as you can see, it's already pointing to the next instruction. The next instruction was add R0 and R1. So on rising edge, instruction is copied to instruction register and forwarded to instruction decoder. Instruction decoder sets all control signals. And let's go to general purpose register. So address number 0 is 0, but address number B, for some reason, is 3. Maybe there's a mistake in my code. So we wrote add R1 and R0. So address number B should have been selected to just 1. So maybe I have a mistake here. Let's go. 0, 0, 0, 1. 0, 0, 0, 1. Okay. But here we have 3 for some reason. Let's check out. Whoopsie. Oh yeah, here I have a little mistake. So I need to go to instruction decoder and actually connect it, instead of connecting here, to bit number 2, like this. So we did have a mistake in the CPU. Okay, now it's pointing correctly. Let's see if it has been updated here. The CPU instruction decoder is correct. And now if I go to CPU and click on this line, it says line number 1. Okay, so it has selected address number A, and for writing 0, address number B is 1. So it has selected register 0 and register 1. Also, in arithmetic logic unit, operation number 0, which is just addition, is selected. Program counter is 2, it will be written to 3, and on falling edge, instruction is performed. So let's go to general purpose register, and we see that register R0 value is B, and in decimal, let's see, programmer hex B is 11. So 6 plus 5 is 11, obviously. Okay, now let's go to CPU. Okay, to MPU. Now I do rising edge. What's the next instruction? It's compare R0 to R1. So comparison does the subtraction, but does not write to general purpose register. So write enable to general purpose register is 0. So let's see, CPU status register value is 0. Let's perform the subtraction. I perform it. Status register changed to 1. What does 1 mean? Let's see. So signed overflow didn't happen. Negativity flag is clear. 0 flag is clear, and carry is set. So probably there was some overflow. Let's see. We compared register R0 to R1. So B minus 6. I don't know why it's carry or overflow 1. But anyway, status register value is 1. Let's see. And when we do the branch instruction compares bit number 1 to 1, and if they were equal, it would branch, but since they are not equal, then it will not branch. So was a useless instruction. So it didn't branch, program counter incremented by 1. So that thing works. Next is CPU. So 4003 is store. So what we hope happens is on rising edge, instruction is fed into CPU. As you can see, writing to random access memory was enabled, and address number 3 counting from 0, so 0, 1, 2, 3, address number 3 was selected. Next, in general purpose register, address number 0 is selected as the source, so R0 value B is forwarded as output. We can also click on address number 3, data value number 11, and on falling edge of the clock, the value is stored in random access memory. Next instruction is load from R2 to 3. Load from random access memory address number 3, whatever is stored there, into register number R2. So on rising edge, we enable random access memory, but this time in read mode. So with this load, we have enabled the output to be forwarded here. So B is already output on random access memory. Address, this 3, is fed into address select register. CPU general purpose register has selected register number R2, just as we wanted. Load into R2, so R2 is active. Writing is enabled. Other signals don't care, so program counter will be incremented by 1. So on falling edge, this B was written into register R2. So you can see it here. Okay, the question is what happens next? If we have empty flash memory, just all zeros or all ones, the problem is if you don't do anything, program counter points to the next instruction, it's all zeros. If you backwards translate this instruction, it will actually do arithmetic logic unit, register number 0, add to register number 0. So actually, this combination is a legal instruction. So if we do another clock, we will see that register number 0 was incremented. So in calculator, plus 11 equals 2 in hexadecimal 16 or 22. If we do one more clock, it again did additions. So we go into this register R0 and it says 2C, right? So it doubles every time. So plus 22, 2C in hex. So this is a real problem in microcontrollers, that after you finish your program, it starts to execute some unknown stuff that is at the end of the flash after your program. So the question is, what do we do? And the answer is, at the end of every program, there is something called end, jump, end. So basically what we tell our microcontroller to do is just jump back to this line. And it jumps back to this line. It says jump back to this line. It jumps back to this line, jump back, and basically this is something that is equivalent to while true in C programming language. Basically, it just executes the same line all the time, billions of times. This is a determination of a program. Theoretically, some processors have this sleep instruction where you can basically say it to sleep or to shut down, but simplest processors don't have such instruction. So all programs, and even if it had, what if it wakes up? All programs have this end, jump, end at the end, automatically appended by a compiler or by a programmer. So we will also do this. And to do that, we need to tell to which line the jump instruction should jump. And so this line was line number 0. This is line number 1, 2, 3, 4, 5, 6, 7. So jump end would be jump to 7. So line number 7 says jump to line or instruction number 7. Since all instructions are one line, then it's the same thing. So jump to address number 7. Let's try to translate it to assembly language. So jump is 0, 1, 0, 1. Next bits are just zeros, they're not used. And line number 7 is 0, 0, 0, 0, 0, 1, 1, 1. This is 7. And in hexadecimal is 5, 0, 0, 7. So in the code, edit contents, I write 5007 here. I press reset, so we reset the program. As you can see, reset signal does not reset random access memory. And let's perform the program once more. So, and as you can see, when we have arrived to the last instruction, which is jump to instruction number 7, on a rising edge of the clock, instruction is read into instruction register, and all signals are forwarded. And check out what happens here. Force jump signal is high, and therefore, instead of program counter +1, which would be 8, a number 7, which is the bottom 8 bits of the instruction, will be forced into program counter. So between 8 and 7, this multiplexer, which is force jump bit controlled, selects 7. So basically, program counter will be stuck on number 7 forever, and it will just keep executing instruction number 7, which is jump to line number 7. And therefore, no matter how many times we press clock, after we have finished our program, it just gets stuck on the last instruction and does not go into unknown territories, into uninitialized flash code or something like that. This is basically, by modern compilers, it's automatically added to your code, even if you don't know it. And in assembly language, you have to add this line yourself. So that is all for today. I think that we have a working CPU with memories, so it's like a working MPU. And in the next lessons, we will already start writing some assembly code, you know, training assembly language. So that's all for today. And actually, what you should do is you should maybe try out other functionality of the CPU to kind of really check out if this CPU works with other instructions as well. So this table I will put in Artus, but you can actually just write it yourselves. It's just a lookup table for all instructions, their contents and instruction codes, and full reference is here. All the instructions with their explanations, I will put them in Artus so you can check it out. There will be push, pop, call, and read, but those ones we will study a little bit later. Okay, so that's all for today.